Hello everyone, our group topic is R and Shiny modeling for predicting heart disease by personal key indicators. These are our group members. Our content is divided into 5 sections. We will introduce them one by one. The dataset is from the CDC, which analyzes the cases of heart disease. We have sorted and filtered out some valuable samples and variables. These are the variables we select. The number of dependent variable heart disease attributes known in the data is 4 more than yes. The dataset is unbalanced, so under-sampling or over-sampling can be used to balance when processing the data. Here we come to the second part, introducing the R packages. The choice of machine learning approach is determined after analyze the nature of the dataset. When dependent variables are in the dataset in supervised, regression can be used if dependent variable is continuous, and the classification can be used for the discrete dependent variables. When the dependent variable are missing from the data, means no supervised, the relationship between variables can be examined by principal component analysis, and the relationship between sample can be explored by using cluster approach. The dataset we select is the one with discrete dependent variable. Therefore, we choose to analyze the dataset in a classification approach. The following packages we need to use. The mailing packages are used for processing the Shiny system, random forest, SVM, naive Bayes respectively. Random forest mode is based on the logical of decision tree mode. Random refers to different decision tree modes. We have random selection of sample from the training with put backs and train a random selection of features. This is because at the beginning of the training, it is difficult to distinguish which sample are anomalous and which attributes have most impact on training result. The result of random forest are determined by voting, and the final result is the classification result the most decision trees agree on. The random forest has advantages of requiring less training time, being less prone to overfitting, and being capable of handling high dimensional of data with more features. The random forest packages is often used to solve problems such as machine learning. The entry in the code of random forest is used to indicate the number of decision trees, and the MAT514 is used to denote the number of variables available for each node. In SVM, we want to select the line with the maximal classification identified for all samples. We do not have to count all of the samples in this procedure. Simply identify the samples along the line and move them as far away from the line as possible. The samples determined the line are called support vectors. When the sample distribution intersection with the margin, we need to find the line that minimizes the distance between the sample vector and the margin. When sample distribution cannot distinguished by straight line, it can be mapped a space that can be distinguished by straight line. SVM have many advantages and applications in the real world. When using SVM function, we may select different types based on different samples. CIS classification is used for classification modes, and EPS classification is used for regression modes. In addition, one classification is used to find abnormal values in sample data. New classification and new regression are different from C classification and EPS classification in terms of the hyperparameter values of the mode. And the kernel function type can be adjusted in the kernel term. Linear kernel, which is simple and interpretable, but can only serve linearly different problems, and polynomial kernel, which serve non-linear problems and automatically set the power, but it is not suitable for large order of magnitude. Gaussian kernel can be mapped the infected demonstration and has variety of decision boundaries, but that contribution is slow and prone to overfitting. Naive Bayes is a supervised machine learning algorithm based on Bayesian that serve classification problem applying an probabilistic approach. It is called naive Bayesian because it considers each predictor variable independent of any other variable in the model. The E1701 package is required to solve the naive Bayesian problem. The following is a brief description of additional R packages.
Before modeling, we need to pre-process the heart disease indicator dataset. Firstly, let's load the data and then check the data structure by using strm command. And we found that the data set contains 14 category variables and 4 numerical variables. Secondly, by checking missing values, we can find that there are no missing values in the data set. Next, let's convert the category variables to factors so that we can contain the different attributes in the variables by summary command. And then checking the statistics of each variables, the aim is to find that if there are any outliers, we can remove them if they occur. Finally, we need to all observation samples are randomly assigned to the train site and the verification site according to the ratio of training site account for 17% and verification site account for 13%. Then we start to use Shining package for website design. The first part of code can be used to cite the title, and the second part of code can be used to cite the panel options for each category variables. The result like the right figures show, and in the same way, we use the same format for the numerical to cite type. Finally, we design the main panel to random images. Then we start design the machine learning panel. It starts with the panel title, and we set the parameters of training samples. Random forest SVM algorithm. Users can adjust the parameters based on their needs and form different visual results. One thing to note is naive-based models don't need to cite any adjustable parameters. Okay, let's look at Step 6. The meaning of this line of code is to take the number of training samples as unadjustable parameters and set the data range to 1,000 and 10,000 so that users can customize the training set size. The initial value here is 1,000. And in Step 7, we set the number of independent variables input into the random forest model range from 1 to 17, and the number of decision trees. Users can select the number between 100 and 1,000 as the number of decision trees in the random forest model by n-tree command. The initial value is 500. For the SVM model, the adjustable parameters are the hyperparameters log C and log sigma. In the Gaussian kernel, whose value range from -5 to 5. Finally, in the Step 9, we added execute button so that users can rerun the model after citing parameters and render different graphic results. Okay, now that we have finished the UI input setup, let's go to serve code to visualize the website page. The first step to assign value to category variables tells the website page where to occur the variables and plot by ggplot package. And not if the variables is age and gene health. They are category variables with multiple attributes and that require placing more legends with plot grid command. So numerical variables execute the same process. Now we can see the results of exploratory data analysis. Users can adjust the options on the left to show different variables with heart disease. Among them, for discrete independent variables, it focuses on the proportional relationship. So, histogram is selected, while for continuous independent variables, it focuses on the chain tree. So, density curve is selected. For data display, we are commented to use shining to show the relationship between each variable and the dependent variable of heart disease. Next, we come to serve code for the machine learning because the data set is unbalanced, which means heart disease patient sample size is far less than that of person without heart disease. So those package here is called to balance the data. In the new synthetic data set, the observation samples with heart disease and the samples have no heart disease are balanced. For the evaluation stage of machine learning results, we are committed to using Shining to visualize the evaluation results. Here we select the ROC package and plot package to draw the ROC curve and AOC diagram of three models. Draw them into the same graph, which is convenient for users to analyze the results of model prediction. Finally, we add histogram of value matrix to show the accuracy of three models. In the test dataset, let's run the last line of code. We can correct a Shining visualization web page. Okay, that's the end of code citing. We can check the output of diagrams in this graph. The related result analysis will continue to introduce you in the next section.
Okay, let's start the results part. Before we start to check the results, we can watch a video and I will show you how the Shining dashboard works. Here we go. Let's access the website and modify the number of variables shown in the Exploratory Data Analysis panel. In the left panel, we can select category variables and numerical variables as well. Let's select smoking and age from category variables. And for numerical variables, select BMI and sleep time here. There it is. We can clearly observe the distribution of these variables. Then, looking at machine learning panel, in the left panel, we can determine how many training set or machine learning parameters to be input the most. After adjusting, click the button to run it. So we can read the values and then compare the model accuracy for these three algorithms. Then we can have a look on the results based on binary category variables. These groups are more likely to suffer from heart disease. They are smokers, stroke survivors, individuals who have trouble walking or ascending stairs, males, those who do not engage in any type of physical activity or exercise, and people who have previously had kidney disease. The following groups are more susceptible to heart disease based on multi-attribute category variables. They are individuals over the age of 80, white people, and have had diabetes in the past, as well as those who believe their health is poor or fair. From numerical indicators, people feel uncomfortable on their mental health and physical health in past 30 days might have higher risk of getting heart disease. As we mentioned in the previous section, we can adjust the value of an algorithm's parameters. Therefore, at which value should the parameters to be set in order to compare the performance of each algorithm? The answer is applying the best parameters for each algorithm. For example, in random forest, just keep the number of trees at 100 because values larger than 50 have the similar performance on results. For SVM, the best parameters for cost and kernel-wise are 2 and 1 separately. Okay, let's look at the model's performance at its best point. You may be wondering what AUC stands for. It's the area under the receiver operating characteristic curve. For example, the AUC of the SVM algorithm is 80%, indicating that 80% of the data in the test set can be predicted. As shown in the graph, we can see that SVM, random forest, and naive Bayes all have a close AUC value, indicating that their classification capability are similar. Now checking the evaluation metrics. There are 5 metrics to help us determine which algorithm performs better. Here, we provide the calculation method for each metric. In general, they can all be calculated if the value in confusion matrix is known. Let's look at the results directly. We observed that the naive Bayes, random forest, and SVM performs at the same level in all of the 5 metrics, except SVM has higher recall. That is, the SVM can predict higher proportion of heart disease patients among all existing patient samples. Overall, based on the comprehensive performance, the 3 algorithms have the same level of performance in our case. Here are some of our references. So this is the end of our presentation. If you have any question, please feel free to contact my team. Thanks for your listening.